Good afternoon, everyone. I thank Professors Uday and Rachel for the invitation to speak at the Electrical Engineering Research Scholars Symposium 2024. When they asked me to give a talk related to the history, I was in a dilemma on what to talk about. My knowledge on the history of electrical engineering is very spotty across different areas. I also was not sure whether the topic I would choose would be interesting for all. So, I finally decided to talk about mathematical modeling as it is an indispensable part in the design and manufacturing of any engineering product. More than half of the talks given by students earlier today were on some mathematical models. But today, I will be talking about astronomical models. You may be wondering why astronomy? Celestial bodies have always fascinated humans from prehistoric days. Astronomy and mechanics were the areas where mathematical modeling was first successful much before electricity and magnetism. So, this is the outline of my talk. First, I will give a layman's understanding of a model. Then, we will see three historical case studies from astronomy. Philosophers had always worried whether what appears to us through perception is real or is there a hidden reality. First, I will talk about a model which prioritized appearance over reality. Next, I will discuss a case to illustrate what happens when your model does not agree with the observational data. What will you do? Will you abandon the model or fix it? In the third case, I will discuss about someone who got overconfident with the past success and became too rigid to entertain other possibilities. My hope is that once you understand these cases, you can identify similar incidents in electrical engineering or other areas. To illustrate this, I will talk about a small meeting of Freeman Dyson with Enrico Fermi. I will conclude the talk with some food for thought. I am sure all of you have used some models in your coursework or research. Some of the models one uses are physical, which are miniaturized versions of large physical systems. However, the majority of models in science and engineering are mathematical in nature. For example, in basic electrical engineering courses, we have used equivalent circuit models of physical components like transistors. What a model provides is an accurate and economical representation of something. It gives us an ability to predict or control behavior even though there may not be any structural similarity between the model and what is modeled. The original motivation to model could be an observation of some regularity or coincidence which resulted in a curiosity to unravel any underlying causal relationship. A true causal model gives one the capability to interpret and predict events. In the past, this was associated with or decided one's position and power in the social hierarchy. Let us see some of the correlations humans have noticed in antiquity. They have observed that the position of the sun in the sky decides the summer and winter seasons. They also notice that the height of the tides vary with the phases of the moon. Both these events repeat annually or monthly. Then there are other events like the conjunction of the celestial bodies, the transit of the celestial bodies across the sun, the retrograde motion of the celestial bodies, and the variation in their brightness levels. These might have coincided in the past with major terrestrial events like deaths, wars, natural calamities, etc. When such events occur, when such celestial events occur, so rulers are always curious whether the celestial bodies are trying to convey any message. Let us look at the motion of the stars. It is difficult to find fault if anyone thinks that sky is a great hollow sphere of large radius surrounding the earth. The distant tingling objects or the stars they appears as attached to the inner surface of the sphere. This, you can call this sphere as a celestial sphere. So ancient people did not know about the rotation of the earth. They noticed that the celestial sphere appears to rotate in a westward motion around a point which is very close to the pole star. This is a daily motion. This happens daily, and it is completed in 23 hours and 56 minutes, which we call as the stellar day. So this motion can be seen in a long exposure photograph of the night sky as shown here. If you freeze the daily motion of the celestial sphere and the stars, the sun appears to wander through the stars and traces a great circle. This great circle is known as the ecliptic. The narrow band of the stars or the constellations which is there in the sun's journey, those are known as the zodiac. Apart from the sun, ancient people have identified 6 more objects which wander among the stars at different speeds. They call the 7 objects as planets. They are the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. They thought that the planets are located on other spheres which are located at different distances from the Earth. But there was another problem. Planets, especially Mars, Jupiter, and Saturn, they show retrograde motion. That is, if you track their position every day, they first appear to move westward for some days, then they move eastwards, and then again westward. Eudoxus, who was a student of Plato, came up with a system of interlocked concentric spheres to account for this apparent motion. But there was another problem. The brightness of the planets also varied during the retrograde motion. So this was a problem for the Eudoxus model. Claudius Ptolemy, who lived in the 2nd century Common Era at Alexandria, proposed an alternative model. In his system, each planet revolves uniformly along a circular path known as the epicycle. The center of the epicycle moves around the Earth along a larger circular path which is known as the deferent. Ancient people, they also have noticed that the speed of the planets, for example the sun, varies as it moves across the zodiac. So in order to explain, Ptolemy introduced the equant and claimed that the planets maintain a constant angular motion around the equant point and not the Earth. The center of the deferent, that is the center of the larger circle, is located at the midway point between the Earth and the equant. Copernicus called equant as the greatest crime of Ptolemy. What was done by Ptolemy and others is known as the saving the appearance. We may not know the fundamental reality, but one should be able to reproduce the observations or appearance through calculations. For example, here you can see how the retrograde motion is modeled. So here you can see somebody looking from the Earth sees the planet is coming here, then there's a retrograde motion here, then it is again going in the westward direction. Ptolemy's calculations were very successful, and this model stayed for around 1400 years. Even though others like Aristarchus and Aryabhatta had suggested heliocentrism, it was never adopted mainstream. There were 2 reasons. The Earth moves at 30 kilometers per second around the Sun. This is faster than any human-made rocket. Still, there is no sensory perception of the rotation or the revolution of the Earth. The true evidence, like the stellar parallax and the Foucault pendulum, was a 19th century discovery or invention. Another reason is that how does one explain the motion of a very heavy object like Earth around the Sun? Aristotelian physics of matter and motion demanded the heaviest of the elements at the center of the universe. If Earth is moving, there should be a constant force pushing the Earth. In short, the Aristotelian Ptolemaic universe was a grand synthesis of whatever the observational evidence, the available physics and logic, and Catholic theology. You can see the picture of how the Italian poet Dante visualized the universe. You can see there is a one-to-one correspondence between Dante's version and the Ptolemaic model. Hell is inside the earth and the seat of the god lies beyond the celestial sphere here. One may now laugh at the complex curve fitting done by Ptolemy and others. But please don't underestimate what many circles and epicycles could do. If you add more and more circles and epicycles, you can fit any two-dimensional shape as shown here. In the 16th century, Copernicus suggested an alternative heliocentric system. He discarded the major epicycles and equant, but he still needed the minor epicycles. Please note that the Copernican model was not accurate or needed less parameters when compared to Ptolemy's model. It was only aesthetically simpler. However, it was noticed that it can create major cosmological and theological problems. If anyone is interested, we can discuss more about it during the question and answer session. So, the popular model in the late 16th century was a model by Tycho Brahe. In Tycho's model, all the planets except Earth revolve around the Sun, and the Sun, along with all the planets, revolve around the Earth. Tycho's model retained the mathematical advantage of Copernicus's model without the cosmological and theological problems. Tycho had a large number of assistants, and with the help of them, they had collected a lot of astronomical observations. These observations were the most accurate ones which could be made possible by naked eye. Johannes Kepler got this data after Tycho's death, and he worked on this data for around 8 years. He tried to fit the orbit of Mars using a circle. The average error was 2 arc minutes and the worst case error was 8 arc minutes when compared to the observational data. He found that it can be eliminated by using an elliptical orbit. So he formulated the 3 laws of planetary motion based on these observations. Kepler's model completely replaced all the epicycles and other complications of Ptolemaic and Copernican models. In early 17th century, Galileo introduced telescopes to astronomy, and he brought more troubles for the geocentric worldview, like the satellites of the Jupiter and the phases of the Venus, which could not be explained by the geocentric worldview. Now let us see the importance of Newton. From Kepler's third law, Newton proposed the idea of gravitational force of attraction, which decreases inversely as the square of the distance separating the planet and the Sun. Then, based on the inverse square law, he derived the elliptical orbits of the planets, which is the Kepler's first law and consequently the second law. Newton's mathematical derivation were without any precedent in the history of science. Until then, it was thought that different rules governed the motion of what is there on the earth and what is there on the heavens. Based on his work, the shape and speed of terrestrial as well as celestial trajectories could be computed for the first time with immense precision. So here you can see the portrait of Newton. This was drawn in 1689, soon after he had completed his magnum opus, the Principia. At that time, he was only around 45 years of old, 45 years. So, viewed retrospectively, Principia was the most seminal work in the development of modern physics and astronomy. Kepler's laws work under the assumption that the mass of the Sun is much greater than that of any planets, and the gravitational attraction between the planets is small. It was noticed that the Jupiter was moving faster and the Saturn was moving slower than expectations. Pierre Laplace, He attributed this anomaly to the small changes in the strength of the gravitational attraction between the two as they crossed each other. Then people became aware about the importance of planetary perturbations. Uranus was accidentally discovered by William Herschel using his reflecting telescope in 1781. He was looking for double stars and first thought it was a comet, but he observed that it was not growing a tail or increasing its intensity. Uranus was this was the first discovery of a planet which was not known in the antiquity. The interesting fact is that Uranus was observed 22 times before by others who thought that it was an unusual star. Soon after its discovery, people started following its orbit. They found out that it was wandering off the course from the expectation. This created a dilemma. This problem is known as the naive falsification in the philosophy of science. That is, will you reject an established theory on the basis of a single non-supporting evidence? Such a scenario comes in the life of every research scholar who does experimental research. Your observational data may disagree with the theoretical prediction. How do one face it? In this case, does the wandering Uranus sound the death knell for Newtonian mechanics? So there are many hypotheses to explain this problem of the wandering Uranus. Some people conjectured that the space beyond the Saturn may have a different density. Some suggested that the gravitational constant, the g, may vary with distance. As the planetary perturbations were already known from the work of Pierre Laplace and others, some people had suggested that there could be a trans-Uranian planet which is influencing the trajectory of the Uranus. Let me talk about the discrepancy between the prediction and observation. So it was around plus or minus 50 arc seconds. For a comparison, the width of the sun or the moon is 1900 arc seconds. So here you can see the picture of Urban Le Verrier. He was a graduate of École Polytechnique. He was among the top 10 in his class. Although he was interested in mathematics, he was given the job of an experimental chemist in the tobacco research division. Later he joined the Paris Observatory when there was an opening. He was someone who could be trusted that he would complete any job that is assigned to him. At that time, Mercury was giving trouble to the astronomers. Le Verrier published his provisional theory of the Mercury's orbit in 1843. So there was a transit of Mercury across the face of Sun in 1845. But the predictions of Le Verrier's theory failed to match with the observations. Mercury arrived 16 seconds late. François Arago was the director of the Paris Observatory at that time. So he asked Le Verrier to work on the Uranus problem. So in the previous slide, we saw there were many hypotheses for the wandering Uranus. Le Verrier discarded the variation of the G and the different material density beyond the Saturn. He suspected that it could be due to some unaccounted mass. Now the question is, where would you place that mass? There were almost 9 unknowns like the mass of the unknown planet, its distance from the sun, the shape of its orbit, etc. Please remember that there were no computers at that time, and some of the popular numerical techniques we use now are yet to be developed. So this makes suggesting a unique solution a tough challenge. After laboring through the calculations for almost 2 years, Le Verrier on August 31st, 1846, he made a call to the astronomers to look at 5 degrees east of Delta Capricorn for an object 3.3 arc seconds in diameter. So none of the French astronomers thought this was an important call to devote some of their valuable telescope time for this task. Disappointed by the French reaction, Le Verrier made a request to Johann Galle at the Berlin Royal Observatory. Le Verrier knew him as Gale had sent his dissertation to him for some comments. On the midnight of September 23rd, Gale, along with an assistant, found an object which is not there on any of the star maps quite near the location suggested by Leverrier. This announcement was a triumph of mathematical modeling. Here was someone sitting on a desk doing calculations and predicting what is out there billions of kilometers away. Leverrier became a celebrity overnight. But this created a scandal in the United Kingdom. John Adams made a similar predictions in October 1845. Though he had written to English astronomers like Airy, they did not think it was something that should be put on priority. John Adams also did not pursue it proactively. Though Leverrier and John Adams came up with similar locations, the parameters they had used in their calculations were very different and they were not exact. So here you can see the parameters like the distance of the Mercury to the Sun, its mass, which were used by Leverrier and John Adams, and you can see what is the actual parameters here. So later it was found that the Neptune did not exactly follow the orbit either of them calculated. Both were lucky, as if they had made the predictions 40 years later or 40 years earlier, it would have made them a laughing stock. Emboldened by the discovery of Neptune, Leverrier returned to finish the business with the Mercury's orbit. He was appointed as the director of the Paris Observatory. So, Kepler's first law states that the orbit of the planets around the Sun is an ellipse. If we neglect the relatively weak interplanetary gravitational interaction, then the perihelia of the various planets, that's the perihelia is a point at which the orbit becomes closest to the Sun. Okay, so it remains fixed in the space. But once you take into account of all the planetary interactions, what happens is that the planetary perihelia slowly presses around the Sun. This is true for all the planetary orbits. So Leverrier calculated this rate of precession of the perihelion of Mercury. So he discovered that there is a discrepancy between the calculated and the observed rate of precession, which was around 43 arc seconds per century. So as he was coming from the success of the discovery of Neptune, so it was suggested that the reason for the discrepancy could be a missing planet or planets between Mercury and Sun. Then something interesting happened. Lescarbault, who was a medical doctor come amateur astronomer, he wrote to Leverrier about the sighting of an object in 1859. So Leverrier visited him unannounced and quizzed him about his observation. Satisfied by all his queries, he later announced the discovery of this new planet to the French Academy of Sciences on Jan 2nd, 1860. So Leverrier calculated based on the information given by the Lescarbault. Leverrier calculated the planet distance from the Sun as 0.147 astronomical units, and its period was around 90. The time it takes to revolve around the Sun was around 19 days, and he also predicted its annual transit across the Sun. So Vulcan was a name given to the planet. So here you can see this is a planet, so atlas of a solar system from those days. So you can see this is the Sun here, you can see Mercury here, and between the Mercury and the Sun you can see this Vulcan here. So this announcement actually launched a planet-wide hunt for Vulcan, especially during the predicted days of the solar transit and also during the full solar eclipses. However, Vulcan remained elusive after years of mania, discredited observations and disappointed predictions. The irony was that the size of the proposed planet Vulcan was too small to account for the discrepancy in the perihelion. Leverrier died in 1877. He remained a firm believer of his mathematical calculations. It was only in 1915 the mystery of the anomalous precision rate was solved. Near a massive object like Sun, Newton's theory of gravitation should be corrected by Einstein's general theory of relativity. Einstein did not derive general theory to solve this puzzle, but he showed that the general relativity agrees closely with the observed amount of perihelion shift. The Vulcan episode, which came after the success of Neptune, shows what happens when one pushes the model or the framework too much and proposes the existence of new entities to account for the experimental data. So here you can see young Freeman Dyson, who was already famous through his work on quantum electrodynamics and joined as a faculty at Cornell without a PhD degree. He was working on a model and a theory of nuclear force. In the spring of 1953, he met Enrico Fermi. So Fermi criticized the complexity of Dyson's model by quoting John von Neumann. So what Neumann said was that if he has 4 parameters, he can even fit a two-dimensional shape of an elephant, and if he is given one more parameters, one can even wiggle its trunk. So here you can see this. Someone from this, somebody published this, tried this and published this in the American Journal of Physics in 2010. So here you can see they used 4 parameters to fit an elephant, and when they added one more parameter, they could move its trunk. So 70 years later, we are now in the age of extreme models. I am sure some of you recognize this image. This is Jensen Huang, who is the CEO of NVIDIA. So this is from his keynote address at NVIDIA's GPU Technology Conference 2024, which happened 2 weeks back. There he unveiled their new Blackwell GPUs. So here you can see the Blackwell GPU. This has around 208 billion transistors. So what value if you compare it against their Intel's first microprocessor, which is around 1000 transistors. So in this chart you can see he's comparing different deep learning models, and the top one in this chart is a GPT model with 1.8 trillion parameters. This model was trained on 2000 Blackwell GPUs. Each of these GPUs has around 208 billion transistors. The system consumes 4 megawatt it ran for 90 days to train the model. So the discussion about the energy requirement to train these models and whether the training data is generated ethically is beyond the scope of this talk. It would be interesting to speculate what Fermi or Neumann would have said about a model with 1.8 trillion parameters. Perhaps the mood of the current age is closer to what Deng Xiaoping expressed in 1961. It looks like we are back in the business of saving appearances, as everyone is desperately moving to scale up the computational resources and the amount of training data. Please note that I am neither judging whether any particular model is good or bad, nor do I have any dogs in this race. However, one should be aware whether a model is causal or it can make bold testable predictions, or whether the model can generalize beyond the multi-dimensional space that surrounds their training data. So here are a few things you can ponder about even after the talk. So you don't need to submit the answers. First one is that, is there any connection between epicycles and Fourier series? There is an ongoing debate in the philosophy of science, that is between realism and anti-realism. So you can think whether your model is in the scientific realism camp or the instrumentalism camp. So realism assumes mind-independent existence of essentially unobservable quantities of the parameters in the model. Instrumentalism is a form of anti-realism. It cares mostly about the predictive capability of the model, even if the model cannot explain or is not causal. Okay, next, please try to identify historical cases from electrical engineering where the models are used only to save the appearances, like what we saw how Ptolemy used the epicycles, or when mathematical models showed their predictive power, just like the discovery of Neptune, And finally, the cases where the mathematical model failed spectacularly. That was when we saw the Vulcan was proposed to explain the anomalous precision of Mercury. There is something called the argument of pessimistic meta-induction in the philosophy of science. It states that the history of science is full of theories that were once empirically successful but later were abandoned. So the question is, why should one believe in current theories which will be abandoned as false in due course despite their current empirical success? So your job is to prepare a counter argument. So finally, if you don't want to do any of the listed above 4 tasks, I recommend you to read Ted Chiang's story, The Tower of Babylon. Some of you may know the biblical story. So in this work, Ted imagines a group of people climbing that tower which reaches the heavens in a Ptolemaic Aristotelian universe. So these are some books for further reading. The first one is the Tower of Babylon by Ted Chiang. The second book is on the Copernican revolution. This was written by Thomas Kuhn. He wrote this book before he wrote his more famous Structures of Scientific Revolution. The next 3 books, these are on the discovery of planets, Uranus, Neptune and Vulcan. And the last book is an introductory book on the philosophy of science. This quote is from the obituary of Thomas Kuhn, which was written by his doctoral student John Heilbron. Thank you.